Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 25, The Surface of Planet Earth. Now that we've seen how our solar system formed and how it got to be the way it is, let's study each of the planets in detail. We'll start our study with the terrestrial planets and then move on to the Jovian planets and then finally finish with comets and asteroids. But as we study the terrestrial planets, let's begin with the best studied planet of all, and that, of course, is our home planet, Earth. Here's a diagram showing the interior structure of the planet Earth. And the main parts of the planet Earth are the core of the Earth, which consists of two independent parts, a solid inner core and a liquid molten outer core, a mantle that surrounds the core, and then finally on top of that, a very thin crust. And we'll see some more details of each of these layers in a few minutes here. But one interesting thing about our planet, besides the fact that it consists of the core, the mantle, and the crust, is that the average density of our planet is about 5.5 grams per cubic centimeter. You will remember when we talked about the properties of the planets as a whole, that the Earth was the densest of the terrestrial planets, and the terrestrial planets are denser than any of the other planets, and that makes the Earth the densest planet in the solar system at 5.5 grams per cubic centimeter. But here's the interesting thing. The average density of granite, which is a pretty typical rock here on the continents on the surface of the Earth, is only about 2.8 grams per cubic centimeter. So if the average density of the Earth is 5.5 grams per cubic centimeter, and the average density of granite is 2.5 grams per cubic centimeter, that tells us something about what the rocks below our feet must be like. So go ahead and take a minute inside Learning Catalytics and just use a couple words to tell me what you think this tells us about the rocks deep down at the center of the Earth. So go ahead and take 10 seconds to do that in Learning Catalytics. You can pause the video here. All right, welcome back. What did you determine from this? Well, if the average density of the Earth is 5.5 grams per cubic centimeter, and the density of granite is a little less than 3 grams per cubic centimeter, that means that the Earth can't be made of solid granite. Deep down at the center, the materials have to be much denser than they are here on the surface. And this was realized more than 200 years ago, that the center of the Earth has to be much denser than the rocks on the surface because the Earth as a whole is much denser than the rocks on the surface. And the things, the elements, the minerals that we find that are very heavy and dense like that are the metals. And so it was hypothesized that deep down underneath the surface, the Earth is primarily a metal world, and that comes from this density. Now, the reason that those materials are down at the center of the Earth is because the Earth is differentiated. Early in the solar system, when the Earth was molten, all the heavy minerals, all the heavy elements sank down to the bottom of the Earth, and all the light, less dense material, I like to call it the light, fluffy material, floated up to the top of the surface of the Earth. So the rocks that we have here on the surface are the least dense, the light, fluffy rocks, and all the heavy, dense rocks sank to the middle of the Earth. So deep down at the center of the Earth, we have the core. And that central core, as we mentioned a second ago, consists of two parts. There's a solid inner core that has a diameter of about 2,500 kilometers, and surrounding that is a liquid, molten outer core that has a thickness of 2,250 kilometers. And the inner core and the outer core are composed of iron and nickel. The outer core is molten iron and nickel, and the inner core is solid iron and nickel. So it's a metallic core. The Earth has a giant metallic core to it. Now, models of the Earth predict that the temperature down at the center of the Earth is about 6,000 Kelvin, with a density at the very center of probably around 14 grams per cubic centimeter. And that is, of course, significantly denser than the average density of the Earth, and that makes up for the fact that the rocks here on the surface are much less dense. But think about that temperature at the center for a second, the fact that the center of the Earth is 6,000 degrees Kelvin. That is as hot as the surface of the sun. that is, the core of the Earth, is as hot as the surface of the sun. If you were instantly transported down to the core of the Earth, it would be like being transported to the surface of the sun. The primary difference is the density between the two. The surface of the sun is much, 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 much less dense than 1 gram per cubic centimeter, whereas the density at the center of the Earth is much higher than 1 gram per cubic centimeter. But other than that, they would be equally bright, shining at 6,000 degrees Kelvin. Now, in the next lecture, we will see how we know what the interior structure of the Earth looks like. But I can certainly point out in this lecture that models show us that this is a model that shows us the temperature as we go deeper and deeper inside the Earth. And then the red line shows us the melting point of the various minerals that make up the Earth at each of those layers. And we see that when we get to a depth below the surface of about 2,900 kilometers below the surface, but above that, the temperature is below the melting point, so the mantle of the Earth is solid. But between a depth of 2,900 kilometers and about 5,200 kilometers or so, these two curves switch places. That is, the temperature is higher than the melting point of the minerals that make up that part of the Earth. And that is why the Earth has a liquid core. But then, as the density increases as we get closer to the center, physics dictates that the melting point of the rocks, of the iron really at this point, increases, and the temperature is not that high, and that's why we have a solid inner core. So interesting, even though both the solid core and the liquid core are made of iron and nickel, there is a transition point here where it changes from liquid to solid, because as the density, primarily as the pressure increases, as we sink lower, deeper and deeper inside the Earth, the physics of how iron behaves changes. And even at 6,000 degrees, the same temperature as the surface of the sun, the iron is a solid down there. Well, outside the core of the Earth is the mantle. It's about 2,800 kilometers thick, and it consists mostly of silicate rocks. And what we mean by silicates those are rocks that contain primarily silicon and oxygen. And the mantle really isn't, it's certainly not a molten liquid, and it's not quite solid rock. In fact, it's very pliable or very plastic. The rock can flow very, very slowly over long periods of time, but the rock is neither truly solid nor liquid. And then finally, on top of the mantle, we have the crust, and it is the thin, very, very thin layer on top. It floats on the denser rocks of the mantle below, and the crust of the Earth is about 5 to 10 kilometers thick in the oceans. 5 to 10 kilometers thick is the thinnest part of the Earth's crust. And then on the continents where we live, the continental crust is significantly thicker, typically 20 to 70 kilometers thick. The crust of the oceans is primarily made up of heavier, denser rock called basaltic rocks. We'll learn more about basaltic lava in a little while. And then the rocks that make up the continents are granitic rocks, or rocks that are made primarily of granite and rocks like granite. And they are less dense than the ocean, than the basaltic rocks that make up the bottom of the ocean. All right, that's a quick tour of the structure of the Earth. Now we're going to focus our attention on what's going on here on the surface of the Earth. So our next Learning Catalytics question is, who was Alfred Wegener? So I want you to spend a few seconds, you can pause the video now, go over to Learning Catalytics and just type a couple words about who was Alfred Wegener. All right. I hope you were able to come up with an answer to this. I think it's interesting that Alfred Wegener is responsible for one of the most important ideas in all of geology today, and yet many people don't know his name. He is the scientist who first developed the concept of plate tectonics, the fact that plates on the Earth are moving around. What we're going to study next is the modifiers of the surface of our planet. That is, what are the things that are causing the changes that we see on the surface of our planet? And we're going to talk about 3 of them. We'll talk about plate tectonics in detail, and then we'll talk a little bit about volcanism, and we'll talk a little bit about erosion. But let's start with plate tectonics. So the origin of the idea starts in 1912 with a German meteorologist and a geologist by the name of Alfred Wegener. And Wegener proposed that the continents on the surface of the Earth are moving around. And he proposed this idea. There's a picture of Alfred Wegener. Wegener proposed this idea because he noticed a couple things. First of all, he noticed that if you take a map of the world and you cut the map apart, South America and North America and Africa fit quite well together. If we take North America and Europe and put them in this gap right here, they sort of fill in the spaces and they nicely match up with the boundaries of South America and Africa. And it looked to Wegener like North America, Africa, and South America had once been joined together and that they had since drifted apart. Supporting this was that Wegener realized that fossils that are found in Central South America were also found in Central Africa. And as he looked at fossils around the world, he found that there were very often fossils found in one part of the world that were found in a very distant part of the world as well. And he realized that the reason those fossils were found in such different parts of the world is that those parts of the world were once connected, but have since moved apart. Now, unfortunately for Alfred Wegener, his idea was ridiculed at first. And I'm sorry to say that when Alfred Wegener passed away in 1930, his idea was still being ridiculed. And the reason that Alfred Wegener's idea that the continents were moving around was ridiculous has to do with how you propose paradigm-changing ideas in science. These are ideas that are radical changes from the existing knowledge in science. Carl Sagan put it best when he said that extraordinary claims require extraordinary evidence. And in Wegener's case, he was making an extraordinary claim. He was making the claim that the continents on the Earth were moving around. And that was contrary to all prior experience and all prior knowledge of the surface of the Earth. The continents were monstrously huge. They were monstrously heavy. Scientists didn't believe that there was any way they could be moving around. To make his case that there was to make his extraordinary claim, Wegener needed to provide extraordinary evidence. And the problem is that Wegener's idea that the continents once fit together, although we now know that this was true, just didn't rise to that level of extraordinary evidence that was required to change the belief that the Earth's continents were sitting still, that the Earth was not dynamically changing like this. It wasn't, in fact, until after World War II, and primarily in the 1950s and the 1960s, that evidence started to accumulate that the continents are, in fact, moving around. And this came from a couple different sources. First of all, it came with advances in geophysics in the 1940s and 1950s, seismometers being able to measure what was going on underground. It also came with surveys of the oceans. During World War II, submarine warfare played a major role in the war. It was realized after the war that nuclear submarines would be a major strategic asset for nations across the world, and to make use of those, nations had to map the ocean floor. And what they found is that the ocean floor wasn't just a flat abyssal plain that had nothing on it. In fact, deep down at the bottom of the ocean, there were huge mountain ranges that stretched across thousands of miles, very tall mountain ranges that jutted up thousands of meters above the bottom of the ocean. It was also realized that there are faults on the surface of the Earth, and that on many of these faults, as we now call them, the plates are moving apart or sliding next to one another. In the 1950s and 1960s, extraordinary evidence was gathered that, in fact, plates are moving on the surface of the Earth. And it really wasn't until the 1960s that the idea of plate tectonics was beginning to be widely accepted. And I would argue it really wasn't until the 1970s that plate tectonics became standard curriculum in most geology classes. And today, of course, plate tectonics are realized to be probably the defining feature of geology on the surface of the Earth. And I think it's remarkable that it was really only added to the geology curriculum about 50 years ago. And that's, again, because this extraordinary claim that the continents are moving around required extraordinary evidence. And unfortunately, Wegener just didn't have access to enough data to prove to the geologists of his time that the continents were moving around. Okay, So let's talk a little bit more about this continental drift or plate tectonics. The continental plates are riding on solid plates of the upper mantle. This is called the lithosphere. Litho means strong, and these are the strong upper crust and the upper mantle. So you'll notice that in this diagram of the Earth, there is the mantle right here, and then above that is the rigid mantle. The rigid mantle is the lithosphere. That is the hard, tough upper part of the mantle. It's riding on a plastic part of the upper mantle called the asthenosphere, which is the weak layer. So this weak layer means that the rocks are quite pliable, they're quite plastic, and they can move around. And the rigid mantle above that are solid, rigid plates that are moving around on that softer underpart. And altogether on the surface of the Earth, there are about 8 large plates and about 24 smaller plates that are moving on the surface of the Earth. And you can see some of them here. You can see the plates laid out. So there are things, for example, the North American plate, the South American plate right here, and many, many different plates, about 8 large plates and lots of smaller plates across the surface of the Earth. Okay, so what happens as these plates move around? Well, if the plates are moving around, there will always be places where the plates collide with one another. And typically, when an ocean floor plate collides with a continental plate, the ocean floor plate, being made of that heavier, denser rock, will get pushed underneath the continental plate. So here's an example. Imagine here in the Pacific Ocean and South America, where the Pacific Ocean plate and the South American plate are actually being driven together. As the Pacific Ocean plate collides with the South American plate, the rocks that make up the Pacific Ocean plate are heavier, denser basaltic rocks, and they are much denser than the granitic or granite rocks that make up the South American continent. So when those two collide with one another, the ocean plate gets driven underneath the continental plate. Where the two of them collide with one another, a deep trench forms. And off the edges of many of the continents, we see a deep trench called a subduction zone. And that is where friction between the oceanic plate diving underneath the continental plate is dragging the continental plate down with it, right? The friction where those two are meeting is dragging the continental plate down as well. And it generates a very, very deep trench in the ocean. Now, as this ocean plate is driven deep down into the upper mantle, it gets much hotter down here. That material starts to melt, and some of the lighter rocks, some of the less dense rocks that are molten, actually, because they're less dense now, they're buoyant, and they actually rise up to the surface, up into the continental plates, and they can erupt on the surface as volcanoes. And it is these colliding areas where plates collide with one another that we often find mountain ranges, and in particular volcanoes interspersed with mountain ranges. So they can push mountain peaks up, and they also create volcanoes. A really good example of this is Mount Vesuvius. So here is Mount Vesuvius, an example of a volcano that forms over where two plates are colliding. As we will see in a little while, this is an example of a stratovolcano. And deep down underground here, the ocean plate is diving underneath the continental plate. It's getting melted. That molten material is rising to the surface. And as that molten material pokes up through the surface, it creates a volcano. So this rising molten material is responsible for the volcanic activity that we often see around the edges of plates. Around the Pacific Ocean is a ring of geologic activity called the Ring of Fire. This is where we find many of the world's volcanoes. This is also where we find some of the world's significant mountain ranges. And these are around the Ring of Fire because this Ring of Fire is where continental plates are colliding with ocean plates. So, for example, here in South America, as the Nazca Plate and the South American Plate collide with one another, as the Nazca Plate gets driven underneath the South American Plate, it pushes up the Andes Mountains and also creates all the volcanoes that we find in and amongst the Andes. It's responsible for the Cascade Mountains in the Northwest, including all the volcanoes that we know there, such as Mount St. Helens and Mount Rainier. So it's responsible for mountain ranges such as the Andes in South America and the Sierra Nevada in North America. So we find a lot of mountain ranges around these boundaries, and we also find a lot of volcanoes, such as all the volcanoes in the Aleutian Islands of Alaska and then over here in Eastern Asia. When two plates don't directly collide, but they slide along one another, we can get a slip fault or a strike slip fault, and that's something like the San Andreas fault. So in the case of the San Andreas fault, we have one plate moving to the north, another plate moving towards the south, and these two move past one another at a rate of about 1 inch per year on average across the whole length of the San Andreas fault. What happens typically with these faults, though, is that they don't move smoothly across one another. Friction causes them to hang up on one another, and tension tends to build and build and build. And then suddenly there's a giant earthquake as that friction suddenly lets go, and the two plates rapidly slide against one another. We'll end up with a massive earthquake and a huge motion. And then the tension will start to build again and again until the next great earthquake. Now, there are also places down at the bottom of the ocean where the plates are pulling apart. Deep down at the bottom of the Atlantic Ocean, for example, is a mid-ocean ridge called the Mid-Atlantic Ridge. And it's an area where mantle material is rising up. It's dividing the ocean plate, pushing the ocean plate apart, and creating a mountain range down at the center of the Atlantic. So here's the eastern seaboard of the United States. Here is Europe over here. And cutting down the middle of the Atlantic Ocean is a giant mid-Atlantic ridge. And this is a place where a hot material from the mantle is rising up to the crust. And as it rises up, it pushes the oceanic crust to the west and to the east. So some of it is spreading to the east and some of it is spreading to the west. And this in part is pushing the continents around, and it's also building a giant mid-Atlantic ridge at the center of the Atlantic Ocean. Currently, right now, about 2 square kilometers of ocean floor is created every year on the surface of the earth. And this is like a giant conveyor belt. You're creating new ocean crust here, and that's pushing outward like that. Typically, it takes only 200 million years to replace the entire seafloor. So the entire bottom of the ocean is replaced every 200 million years. Now, that sounds like a long time, but keep in mind that there are rocks up in Canada and Australia that are 3.8 billion years old. The rocks that make up the Appalachian Mountains here on the eastern seaboard of the United States, the core of those mountains are 1 billion years old. So that means that the oceans, the bottoms of the oceans, are relatively young compared to many of the continental rocks that we see. And that's because it doesn't take long for this conveyor belt to completely replace all of these rocks at the bottom of the oceans. So you can also imagine if new rocks are being born here at the Mid-Atlantic Ridge, that is, they're being pushed up and the seafloor is spreading to the west and to the east. As we get further away from the Mid-Atlantic Ridge, the rocks will get older and older. And sure enough, we see exactly that. Here is the middle. This is a plot of a piece of the Mid-Atlantic Ridge just south and west of the country of Iceland. And here is the ridge axis, and rocks that have been sampled from the bottom of the ocean indicate the ages of these different rocks. And what we find is that the rocks here along the ridge axis are quite young, 2 million years old or less, and as we get further away from the ridge, the rocks get older and older. These rocks are about 6 million years old, these are about 8 million years old, and these are over 10 million years old. A perfect example that new rocks are being created in the ridge, and they're getting pushed away, and as they get pushed away, as they get older, new rocks are always coming in on the ridge. This ridge is probably driven by convection deep down inside the earth, where hot material is rising up, creating the ridge and pushing that ridge, pushing the ocean floor side to side, so moving those two plates side to side. So on average, with plate tectonics, the continents are drifting apart at an average rate of about 2 centimeters per year. So that's a little bit less than an inch per year. If you work out the numbers, that's 2,000 kilometers in 100 million years. Now, when two continents, and as evidence of that, going back to Alfred Wegener's original idea that South America, Africa, and North America were once joined together, probably 200 million years ago. Many of the continents were joined together, and they have since separated over time, since they were once joined long ago, hundreds of millions of years ago. And that is an example of Pangaea, this time when all the continents formed essentially one giant continent on Earth. That giant continent was called Pangaea. Now, when two continental plates collide with one another, neither one can sink below the other, and in that case, we get some of the tallest mountain ranges on Earth. Here is a case where the Indian plate is colliding with the plate underneath Asia, and this is a continental crust plate. The Asian plate is a continental crust plate, and because neither of those are heavier or denser than the other, it will not sink below. And as these two plates are being pushed together and colliding with one another, they are pushing up the tallest mountain range in the world, and that is, of course, the Himalayan mountains. So the Himalayans are the result of two continental plates getting pushed together. The Appalachian Mountains here on the east coast of the United States were created when the North American plate repeatedly collided with the South American and African plates hundreds of millions of years ago. As they would collide, they would push up these mountains. Erosion would wear them down, but another collision would happen and they would get pushed up again and eroded down, and another collision would happen. There were multiple episodes of mountain building here on the east coast of the United States. But it has been hundreds of millions of years since that over 200 million years since that last collision. And that means that the Appalachian Mountains have been wearing down now for 200 million years, which is why they look so different than the Himalayas. Though hundreds of millions of years ago, they may have been as tall and as ragged as the Himalayas. Now, every now and then, continental plates are pulled apart. We've seen what happens down at the bottom of the ocean. When the oceanic plate gets pulled apart, we get a mid-ocean ridge. What happens when a continental plate is pulled apart? Well, when continents get pulled apart, they thin out in the middle and they open up giant rift valleys. So a really good example of this, probably the best example on Earth today, is the Red Sea. So the Red Sea is an example of where the African plate and the Arabian plate are pulling away from one another, and they're opening up a giant rift valley on Earth. So the Arabian plate and the African plate are pulling apart. That's allowing new material to well up underneath, but also as they pull apart, the crust thins, the plate thins, and water is allowed to flow in. And this is the Rift Valley that we have. This is the Red Sea as we have it right now. As these continue to pull apart, this will eventually widen and become a mature ocean, such as the Atlantic Ocean. When it first starts spreading like this, we get a rift valley. And the best example of a rift valley on the Earth is the East African Rift Valley right here. This is a place where the continent is pulling itself apart. And what I think is really fascinating about this rift valley is it's visible in satellite images of Africa. You can actually see evidence for the rift valley right here, where the continent of Africa is getting pulled apart. So these mark the different rift zones in Africa. But basically what's happening here is the plate underneath the Indian Ocean is pulling this way, the African plate is pulling that way, and this material is thinning and breaking apart. At the same time, the African plate is moving this way and the Arabian plate is moving that way, and that has opened up a rift that has become the Red Sea. So the Red Sea is an example of a rift valley. In this case, it has filled in with water. In the case of Africa, it has not yet filled in with water, but eventually will probably form a sea, and then eventually, as it gets wide enough over time, an ocean. So plate tectonics are one of the things that modify the surface of the Earth. Another thing that modifies the surface of the Earth is volcanism, or volcanoes. And there are two types of volcanoes on Earth. And I want to mention these types of volcanoes because we will see one type of volcano elsewhere in the solar system, and that is the shield volcano. Shield volcanoes are formed over hotspots in the mantle of the Earth. And the rocks that flow up, the molten material that flows up, forms basaltic lava. Basaltic lava is very dark in color, almost black in color. And it's also lava that is very thin and very runny. And for that reason, shield volcanoes don't form the very steep-sided volcanoes. When you're a child and you draw a picture of a volcano, you typically draw something with very, very steep sides. Shield volcanoes typically have very, very gentle slopes to them. And those gentle slopes are a result of the fact that the lava is much thinner and much runnier than the lava that forms steep-sided volcanoes. This particular volcano that you're looking at here, that is Mauna Kea. Mauna Kea is one of the two major shield volcanoes that make up the large island of Hawaii. It's a photograph taken from Mauna Loa, which is the other of the giant shield volcanoes that make up the big island of Hawaii. So these are examples of shield volcanoes. And as I said, they're forming over a hot spot in the Pacific Ocean. And what's interesting is the Pacific Ocean plate is moving over that hotspot. That is, the hotspot is sitting still, and plate tectonics are carrying the Pacific Ocean plate over that. And so what happens is the hotspot works on building volcanoes and building islands, but then the plate moves on and the hotspot has to start over again. As we look at the Hawaiian Islands, we see that the islands to the furthest northwest, such as Kauai, are very much more eroded and very much older than the big island of Hawaii or even the island of Maui. So the younger islands are to the southeast and the older islands are to the northwest. And then, in fact, if we go much farther in the Hawaiian chain, we come to islands such as Midway Island, and these islands are significantly older. They were over the hotspot millions of years ago. And just to the southeast of the big island of Hawaii is Lohi, which is a future Hawaiian island. And millions of years from now, that volcano will finally poke through the surface and create yet a new Hawaiian island down there. So those are shield volcanoes. They're typically found over hotspots on the Earth. You will notice, if we go back to this map of the plate tectonics for a second, you will notice that the island of Hawaii, or I should say the islands of Hawaii, are located right in the middle of the Pacific plate. They are not caused by plate tectonics. This is not volcanoes caused by colliding plates. These are volcanoes that are caused by sitting over a hot spot underneath the crust of the Earth. Volcanoes that are found around the Ring of Fire, those that are found on the boundaries of plates, where plates collide with one another, those are the stratovolcanoes. Those are the very tall, steep-sided volcanoes. So this is one of the most beautiful, most striking stratovolcanoes in the world, and this is Mount Fuji in Japan, right on the Ring of Fire. Stratovolcanoes are made of rocks that tend to be much thicker and don't flow nearly as easily as the basaltic lava that we find in the shield volcanoes. And because this lava is much thicker, the volcanoes can form much steeper sides. So rather than the gently sloping sides of the giant shield volcanoes that we find in Hawaii, we find these stratovolcanoes with very, very steep sides to them. And this is an example of a stratovolcano. And they're typically found on the boundaries of these plates. The last thing I'll mention is that we also find huge lava flows on the surface of the Earth that aren't located around giant volcanoes. These are places where, over a hot spot, where a rift will open up and huge lavas will flow across the surface of the Earth. Probably the best preserved example of this in the United States is Craters of the Moon National Monument. If you ever get the chance to visit it, it's in south central Idaho. It's really a spectacular place to go visit. These are extensive basaltic lava flows that cover hundreds of square kilometers of south central Idaho. And they occurred 15,000 to about 2,000 years ago. And let me just play a quick video here so that you can see a little bit about what they look like. So here's the National Park Service page on the Craters of the Moon National Monument. But it's really a remarkable place where these lavas flowed thousands of years ago, covered hundreds of square kilometers of south central Idaho. Now, because of plate tectonics, that hot spot has since moved, and that hot spot that formed Craters of the Moon National Monument is now sitting underneath Yellowstone National Monument, Yellowstone National Park. And so sitting underneath Yellowstone is that hot spot that formed Craters of the Moon National Monument. All right, so those are three processes or two processes that can affect the surface of the Earth. We've talked about plate tectonics, and we've also talked about volcanism. The last one that I want to talk about is erosion. So in learning catalytics, very quickly, I would like you to list at least three processes that can erode rock. So type in at least three things that can commonly erode rocks on the surface of the Earth. You can list more if you want, but I want you to list at least three. All right, what did you come up with for processes that erode rocks on the surface of the Earth? I would argue that the three primary processes that erode rocks on the Earth are wind, water, rain, and ice erosion. So let's talk about the three of those. Let's talk about an example of water erosion. And I think there is no better example on Earth of water erosion than, of course, the Grand Canyon, the spectacular Grand Canyon. The Grand Canyon has been formed over about 1 billion years as the Colorado River has cut down through various layers on the surface of the Earth. As the West has been pushed up by plate tectonics, the Colorado River has worn its way down through the layers of the Grand Canyon. And down here at the bottom, we find rocks that are 1 billion years old. And as we go higher and higher in the Grand Canyon, we find rocks that are younger and younger. So that is an example of water erosion. Rain is also an example of something that wears away rocks. A second process is wind erosion or aeolian erosion on the surface of the Earth. This is the Great Sand Dunes National Monument or the Great Sand Dunes National Park that is in Colorado, a really spectacular place, a place where you can see the largest sand dunes in North America, the tallest, I should say, sand dunes in North America, a place where wind has clearly been eroding and blowing, eroding rocks and blowing for a long period of time. And then finally, last of all, there is ice erosion because of glaciers and in the past because of ice ages on the surface of the Earth. Typically, when glaciers flow down valleys, they will hollow the valley into a gentle U shape like that. So these U-shaped valleys are an excellent candidate for valleys that once held giant glaciers in them. This is a glacier pictured many years ago that is flowing down, these two glaciers, in fact, this one and this glacier here, combining to flow down this valley and erode it away as all that heavy ice pushes down the valley. Rocks that are captured between the ice and the surface of the rocks will grind away those valleys and grind away those rocks, making valleys on Earth. Finally, all three of these processes, water, wind, and ice, will cause particles to be worn off the rocks, and those particles will eventually wash out into the oceans where they will be laid down as sediments. And sedimentary rocks are one of the most common kinds of rocks that we see on the surface of the Earth because as these sediments get laid down, eventually over time they get metamorphosized or changed into solid rock, and we see rock layers such as this on the Earth where we can see distinct layers inside the rocks. In a couple lectures, we will talk more about these sedimentary layers, and we will talk about what these layers can tell us about how time has passed and how we can use these layers to determine the times at when certain things happen, both on the Earth and on other planets. This process of looking at layers and determining when things happen is called stratigraphy, and it's based on the law of superposition. And the law of superposition tells us that the rocks at the bottom are older than the rocks at the top. And that's because of the way layers are laid down. As the sediments are laid down, these sediments are laid down, these sediments are laid down on top of them, these are on top of them, and these are on top of those. And typically when we see layered rocks like these, unless something really dramatic has happened to turn those layers over, the rocks on top are the youngest and the rocks on the bottom are the oldest. And we'll see more of this layering when we talk about the moon in a couple lectures. But now that we've seen the surface of the Earth, in our next lecture, we will talk about the interior of the Earth and how we know what's going on deep down below our feet. So join me in lecture 26 when we talk about the center of the Earth.